Hi students. So today we start lecture 75 in our aerospace engineering course, and today I am going to discuss the propeller, which is something which you often see in aircraft. In fact, you are likely to see that a very large number of smaller aircraft have the propeller, and propellers have made a big comeback because of the UAVs and the drones which you see flying around. These are often propelled by the propeller. So now the next few lectures are going to discuss the propulsion aspect. So we will first focus on the propeller, then on the jet, and then on the rocket, and so on. I'm Dr. Ranjan Ganguly. So if you see a propeller aircraft, you should take a good look at the propeller itself, because that's something which is very important for this aircraft. It's what is propelling it forward. Now you can clearly see that the propellers are of various types. So you generally have 3-bladed, 4-bladed or 5-bladed propellers, depending on the particular problem you have, the amount of thrust you want to generate, and so on. And whatever be the number of blades in the propeller, the basic physics is the same. And today we are going to discuss how this propeller is going to produce thrust. So that's the primary aim of the propeller. The aim is to produce thrust so that you move in the forward direction, and of course the drag is acting behind it. So if you want to fly, you must balance the drag with the thrust. Now let us look at the propeller from the front view. So in that case you will clearly see that there is a hub here, that's this region here, and then there are the blades here. So these are known as the propeller blades. So most of the cases you may have 3, 4 or 5 blades, and 3 blades are actually quite common. And in case you take a particular blade and you look at the section or look at the cross section of the blade, you will find that this is an airfoil cross section. Now these airfoil cross sections are somewhat different from the ones which are used in typical fixed wing aircraft. They are specifically made for propeller aircraft and so on. So we'll look at that in detail in today's lecture. Now, of course, the velocity V infinity is coming from front, and what happens is that the propeller rotates and then it produces a thrust in this direction, and that propels the aircraft forward. So let's start looking at the propeller from different views. So this is the side view of the propeller, and of course you see the hub here and you see two propeller blades, for example. Now the velocity comes from the front, that is V infinity, and we can take any section on the blade, and that is at a distance r from the center of the hub. So this is something to remember, because these blades are rotating and there is going to be a rotational component of velocity also which acts on this particular section. That plays a very important role in the propeller aerodynamics. Now let's look at two sections. Let's look at a section near the tip and a section near the root. Now what we will often see in propellers is that at the root the blade pitch is going to be more, and at the tip it is going to be less. So this angle beta is less, this angle beta is typically more. So what happens is that this beta is a function of r, or the radial station, and therefore propeller blades tend to be highly twisted. At the end of this video you will understand why this is so. This is something which is required for the aerodynamics. So let's now look at some of the propeller nomenclature or notation. So you typically have the propeller airfoil like this. It's got a chord line, and then you have some components of velocity. So the forward velocity is like this. So that is V infinity. Also, like I mentioned, there is a radial component of velocity, that is R omega or omega R, where omega is the angular velocity of the propeller. Typically you express it in terms of radian per second. So if you have this value in RPM, you can convert it to radian per second easily. Now the result of this V infinity and R omega is that you have a resultant velocity V which acts in this direction, and this velocity V is at an angle phi with respect to the horizontal here. Now there are two more angles here. There is beta, which is the pitch angle, that's between the horizontal and the chord line, and there is also the angle of attack alpha, which is given by the angle between the resultant velocity v and the chord line. So we can very easily write from geometry that phi is equal to beta minus alpha. or you can write phi plus alpha equals beta, and so on. So these three angles are essentially related. So this is the basic diagram as far as the propeller is concerned, and the net result of this velocity v is going to be that there is going to be a lift, there is going to be a drag. The lift is normal or perpendicular to the velocity v, and the drag is parallel to the velocity v. And of course what we are interested in is thrust, but that we'll discuss pretty soon. There is an angle phi between the lift and the thrust, because the thrust, remember, this vertical direction corresponds to the forward direction of the propeller. So the v infinity velocity is coming like this, so your aircraft is flying in this direction, so thrust has to be generated in this direction. Now why do we have high twist will become clear later on, but you can clearly see one issue here is that beta itself is a function of r, and we will also see that phi is a function of r, because you can clearly see here that whether you are at the root, whether you are at the tip, r is going to vary, and so the angle phi is going to vary. So one of the objectives in propeller design is to keep alpha such that at different radial stations you have a reasonably good value of alpha, which is required to produce lift. And therefore what happens is that beta varies along the span. So this beta is r is pitch angle is a very important concept in propellers. If you are interested, you can go to any air show or any nearby airport if they permit you, and see some of the smaller aircraft which happen to be propellers, and you will often see the high twist which is inculcated into them. So let us now return to this picture. Now of course we know some things in detail. We know that the velocity was coming from front, and we also know at the tip r omega is high because r is larger. At the root r omega is low because r is smaller. So therefore at the root the beta angle is more, at the tip the beta angle is less. So typically we can conclude that propeller blades are highly twisted, and beta r at root is greater than beta r at tip. Now, of course, let's come to the whole reason as to why the propeller exists. The propeller exists to create thrust. And so if we now look at this vector t, what we will see that thrust is L cos phi, that is the component of lift in this direction. Cos phi will give you the component of lift along the t direction, minus d sine phi. So that's the downward component of the drag here. Now, clearly, this is something we want to calculate, and this is something which is useful for us because the propeller is generating the thrust. Also remember the previous things which we mentioned, phi is beta minus alpha, so beta minus alpha is phi here, alpha is the angle of attack. And what you have to do is to sum all the t's which are going around the different propeller blades, and the total of that is going to be the thrust here. So some kind of blade element theory can easily be used to get this kind of thrust. So now certain things will become clear to you. Of course, from aerodynamics, we know that because thrust depends on lift and drag, it's going to essentially depend on the value of alpha. So if you have a certain velocity coming, you will have a certain alpha, and depending on that alpha, lift and drag is going to vary, and so Ta is a function of alpha. Therefore it's also a function of beta and phi, because alpha is a function of beta and phi, and so we can write T is Ta, or T is a function of beta v infinity and r omega. So remember that phi itself is a function of v infinity and r omega. You can write phi is approximately equal to v infinity by r omega, or tan phi is equal to v infinity by r omega if you want to be fastidious, and then you will get this equation here. So essentially now we have three things which control thrust. They are the pitch angle, the velocity at which the airplane is flying, and the rotation speed of the propeller. So now we have the available power. We can easily calculate the, or rather I should say we have the available thrust. We can easily calculate the available power, and that's going to be the thrust into the velocity. Now there is one more power which is the shaft brake power, and this is the power delivered by the shaft of the engine to the propeller. So if we divide these two values or these two powers, we get eta is Pa by P. This is the propeller efficiency. So this is a parameter which is very important in propeller design. And if we substitute Pa is TaV infinity into this formula, we immediately get eta is TaV infinity by P. So this is the efficiency of the propeller. So it's something which is very important and we often need to calculate. And of course, in propeller design, you want to maximize this value. Now, of course, in the real world, the efficiencies are always less than 1. Here also the same happens. And that's because there are several losses which take place. So, for example, the kinetic and rotational energy is lost to the wake. So, if you go far downstream and see, you are going to find the air is going to have a lot of rotational energy, lot of motion and so on. So, this is some of the energy which is lost. Also, there is going to be skin friction and pressure drag which is going to be associated with the propeller airfoil itself. Remember, in our earlier lectures, we had a lot of discussion about skin friction drag, boundary layer, and so on. And also, we had discussion about pressure drag. Remember the issues related to separation, especially from laminar and turbulent flow. So, all these contribute to drag, and therefore, there is lot of loss as far as the propeller is concerned. And these are things which do not directly go to create your available thrust. Beside that, there is compressibility loss also. Now, many people are surprised as to why a propeller aircraft which flies pretty slowly is getting compressibility issues. And this happens because the velocity which the airfoil sees is actually a combination of V infinity and R omega. And do remember that many propeller aircraft fly pretty fast, but their rotation speeds are also high and the propellers are also of reasonable large diameter. So what happens is that the velocity v may be quite high, especially near the tip region where r is a maximum. And in these regions, you can get compressibility effects, you can get shocks, you can get all kind of phenomena, and you can get boundary layer separation due to the shocks and so on. Now, we have discussed all these issues related to compressibility before, so this does play an important role, and this is something which limits the propeller speed. So, for example, what happens is that most propeller aircrafts only fly at lower speed regimes because even while V infinity is relatively low, the Mach number is approaching compressibility or near 1 in many of the situations. So you may encounter transonic flow problem even though your V infinity is maybe in the high subsonic regions and so on. So now let's look at an important concept in propellers, and that is the advance ratio. So before we define the advance ratio, let us define something we call the value of n, which is the number of propeller revolutions per second. And you can obtain this straight away if you have omega. So remember, that's the rotational speed of the propeller. So if we write it as 2 pi n, then this gives us the number of propellers revolutions per second. So if you have this, then for a given pitch angle beta and propeller diameter d, eta is a function of this value j, where j is the advance ratio given by V infinity divided by n into d. So this is something which is very important in propeller theory, and that's something we are going to look at now in detail. Now, of course, you know that t is a function of beta, V infinity, and n. So previously we were talking about omega. We can now replace this by n here. Now, if we plot these efficiency values of a propeller with respect to the advance ratio, we get curves like this. And here we have assumed three fixed beta conditions or three fixed pitch angles, beta 1, beta 2, beta 3, which I have color coded here. And these curves go like this as a function of the advance ratio, or you can say as a function of the velocity. And what happens is they go up and they go down, so they have a clear maximum point. And the locus of these points can be a line which I have made here, this dotted line, and this corresponds to eta max, that is the maximum efficiency value. So essentially what happens in each case, the efficiency value goes up at a given beta value and then it goes down. So you actually want to capture this particular value in most cases. The efficiency of 1 is somewhere here. That's something which is difficult to get, but you can get it to some extent at higher beta values. So now we again write all these things down and let us look at just one point on the curve, which is that why are they all going through 0 here? And the reason is very simple. You can clearly see that when V infinity is 0, J becomes 0. So that part is 0 here. And also eta is TA V infinity by P. So eta is also going to through 0. So all these curves essentially go through the 0 point. So when J is 0, eta is 0. Now we are going to look at the other parts of the curve and why they are so. So to think about this, let us consider two cases. Let us consider a case where V infinity is small and V infinity is large. So I have essentially made two propeller sections, and here I have made V infinity small and V infinity large here. Now you can clearly see that when V infinity is small, the alpha value is large because phi is small. But what happens when V infinity is large, the phi value is large and the alpha value is small. So as the velocity becomes larger and larger, alpha is going to become smaller. And if alpha becomes smaller, J becomes problematic, because what happens is that thrust is related to lift and drag in this way. So if alpha is small, then what will happen? Lift is going to be small, so thrust is going to be small also. So the alpha value reduces as J increases, because J will increase when V infinity increases, and corresponding to that, as you see in these two graphs, the value of thrust is going to decrease. So this is something which happens, and so as the value of velocity increases, the thrust can decrease in propellers in this situation. So this explains to you the second part of the curve, that why this decrease starts happening, and this decrease is happening because alpha is decreasing, and finally you are going to reach some point on this curve where the thrust becomes 0. So that's the point which corresponds to the second 0 point of this particular curve. So one of them takes place at J is 0 and the second takes place at some J is some velocity point which is pretty high. So for any particular beta, this will go like this and then it will become 0 here. Now ideally you would like to use these particular points where I have to put these dots here, because these points correspond to the maximum efficiency. So if you have a propeller at a given pitch, beta 1, let us say, you want to use this point. If you have beta 2, you want to use this point. If you have beta 3, you want to use this point here. Now let's take a look at some typical propeller airfoils. Now some shapes are shown here, and you would think, why are propellers, or rather propeller airfoils, shaped in this peculiar manner? Now one of the reasons is that propeller airfoils are designed to minimize the transponic flow effects due to high airspeed near propeller tip. So you see a similarity between some of these airfoils and some of the airfoils we saw for supercritical flow and for high speed flow, transonic flow, and so on. Remember that more and more UAVs are coming up which are using propellers, and UAV propeller design would be slightly different. You would have to use different type of airfoil there to get the optimal performance, because UAVs fly at somewhat different flight conditions and so on. Now let's return to our problem. Now you clearly saw that the pitch beta has a very big influence in the propeller performance, and what happens is that there are two types of propellers. That is the fixed pitch propeller, which is the classical design of the old days, and here what happens is that beta for all sections is fixed geometrically based on the design point. So you may choose a particular design point and you then fix the value of beta at that point. However, we already know that varying the propeller pitch would be very useful. So beta in this case can be adjustable. This is the variable pitch propeller, and in this condition you gain good efficiency at different flight speeds. So you can clearly see the point here. If you have a variable pitch propeller, then you will use these different points here. So depending on the particular velocity, you can use the point which is optimal for that particular velocity. So that's something you will always try to do. So in some way we can say that you want to fly the propeller aircraft at peak efficiency point by varying the beta depending on the particular velocity you are at. That's the concept behind the variable pitch propeller. Now there is one more concept which is widely used in propeller design, and that is the continuous speed propeller. Now here what happens is that you automatically vary the pitch beta to maintain constant engine RPM, and this will take care of many of the problems which take place, because in general you want to have constant engine RPM. So if you are able to vary pitch accordingly, then you are going to get better performance out of this system. So finally, we can say that the efficiency of the propeller, which is a very important parameter, has become quite high because propeller theory is quite advanced, and by use of variable pitch and continuous speed, many of the newer generation of propeller designs can get efficiencies of 80 to 90%, and therefore the propeller aircraft are actually very efficient at the lower speed situations. So let's return to our picture and summarize what we learned today. We saw that the propeller aircraft is something which is quite useful. We saw that they have highly twisted blade, that the blade has a higher pitch near the root section, the blade has a lower pitch at the tip section, and this is done so that the angle alpha seen at different sections is pretty similar and is a good angle for generating lift. We also saw the efficiency of the propeller is given by TAV infinity by P. So TA corresponds to the available thrust, and we also saw the important parameter known as the advance ratio. J is V infinity by ND, where D is the rotor diameter, N is the rotational speed, and V infinity is the forward velocity which is seen by the propeller aircraft. So the important thing to remember is propeller blades are highly twisted, you have variable pitch, and you have continuous speed in most of the newer designs. Now, I'll just tell you that there are a plethora of aircraft out there which are propellers, and most people do not realize this because they often travel in the jet airplanes through airport in their personal travel. For example, I have listed several aircraft here, the air tractors, the different aircraft, and so on. Some of these are civilian transports which can carry a few people. Some of these are crop dusters, so essentially they are used for agriculture and so on. And there are many small and medium manufacturers which make these aircraft. So if you type of each of these name in Google, you are going to see nice pictures of these airplanes and get a good feeling about the propeller airplanes. Now, more such airplanes have come up. Some of them, like the ATR-72, are being used in various transport between, for example, smaller cities. One of the advantages is that they can take off and land at smaller airports also compared to the jets. There is an interesting aircraft, the Tupolev Tu-95. This is a military aircraft, but it has been in service for a very long time and it's still been in service. And the Antonov aircrafts are there all the way ranging from AN-2 to AN-22. These all use propellers and they go a huge amount in terms of sizing. So the AN2 is much smaller, the AN22 is much larger. You also will see some aircraft such as the Mahindra Airvan 8 and the NL Saras, which has the propeller at the end. So if you search in Google, you will get more idea about some of these aircraft. Now, of course, a resurgence in propeller has taken place because you will see a plethora of the UAVs are out there. Most of the conflicts around the world are showing that UAVs are becoming increasingly important in all kind of conflict situations. And you would have seen UAVs such as the MQ-1 Predator, the IAI Heron, the Bayraktar TB2, the TRDO Rustam. You will see pictures of these if you search in Google. And one of the reasons propellers are, of course, useful in UAVs is if you look at the endurance equation, if that is your aim, then it has rho infinity in it. So essentially, if you are flying at lower altitudes near the ground, sea level, which is the case of many UAVs, then endurance of propellers is going to be highest here. So this is something which is widely used by the drones because the drones tend to often fly at lower altitudes, and if you are trying to maximize endurance, that may be useful in these cases. So that was our discussion about the propeller aircraft. I hope you benefit from this video. Of course, propeller theory is enormously developed. There is a lot of compressible theory which goes into it, for example, using compressible Bernoulli's equation and so on. But we are not going to go detail into that in the introductory class. And again, if you are interested, you will find various NASA reports and other documentation through Google where you can get deeper into this problem. So I will end this video now and I will see you in a lecture sometime soon. See you then.